Okay, so we're going to continue with optimization, and here's a word problem. So we have a car B and a car A, and car B is 30 miles east of car A. So if you look at this, here's car B, and it's the moment that car A begins to move 60 miles per hour. So as car B is moving, so is car A. So if we look at this, here's car B, and as it starts moving, they're moving in a different direction. B is going west, A is going north. What will be the minimum distance between the cars? So we want to know what the minimum distance between these two cars are. If this car B is moving 90 miles per hour, while this car A is moving 60 miles per hour. So we know that that one's moving 60 miles per hour. And so we know that it's 30 distance from when they start. So we know that, this is what's going to happen on there. Okay, so we're going to use some calculus to try to figure this out. And so what we're going to do is look at this problem and label it. So what do we have? Some information that's given to us. So we know that the total distance that's given to us, the total distance is going to be 30 miles. That's from the beginning on there. And so this distance right here, so the distance that's given to us right here, that is going to be 30 minus x. I'm just going to call that x, the distance that we don't know. It's going to start at 30, and then whatever distance is here, that's going to be 30 minus x. And then we also have to label this side over here for car A. We don't know anything about it, so we're just, because it's vertical, we're just going to call that y. And the distance between them, we're just going to call that z. And we know that they're going west and this is going north, so we know that this is automatically forming a right triangle, and we have a Pythagorean theorem. So we have a relationship between everything that's happening right here. So what we're going to do is we're going to use that information to find out the information that we need. Okay, so we're going to start with the Pythagorean theorem here. And so we know that it's going to be z squared is equal to y squared minus 30 and plus 30 minus the x quantity squared. So that's what we have there. And so then we don't want to do implicit differentiation. We want to do as little as variables as possible. And so what we're talking about here is that we also have time t, and none of these have time t in it, but we do give some information. So we know that y is actually 60 miles per hour. And so we know that if we have 1 hour, that y is that traveled 60 miles. And we also know that x is going to be traveling at 90 miles per hour. And so that's the distance here and the time on there. And we don't know what the h and the time is going to be. We know that we want to put miles on there. And so we're going to get that distance. So we know that that's the speed that it's going to, but the y is the distance. And the x is also a distance. It's not a rate on there. So we need to change this. And so what we do is, instead of saying hold on. Instead of saying the 60 miles per hour here, what we're going to do is we're going to do 60t, the time that we have there. So now we have 60 miles per hour times the time gives us the distance. 90 miles per hour times the time is going to give us the distance. And that's the distance that we have on there. So that's what we know. So we're going to use that information. But before we do that, I don't want the z to be squared. I want it to be, so we're going to have the square root of y squared plus 30 minus x squared. And then we don't want it to have the y's and the x's. We're just going to make the z in terms of the time being traveled, because that's really what we're trying to answer anyway. And so we're going to get this to be 60t squared plus 30 minus 90t quantity squared. And so now we have everything with just two variables, z and t, and now we have to take the derivative. The problem doesn't look too nice. But we are going to use the chain rule, which is the easier of all the derivatives, and not that we have a choice here. We have to use the chain rule to actually solve it. So we are going to use the chain rule on there. And so I am going to change this. I'm going to get rid of that. Hold on. Let's see. Get rid of that. And I'm going to change that to I'm going to change that to a 1/2. So I'm changing that so we could see the outside function. So the outside function, we're going to get 1/2. And so we're going to then do negative 1/2 there. And what we're going to do is leave the inside alone. And then we have the chain on. So we're going to chain on. We're going to take the derivative of the inside and chain that on. So the derivative of the inside here, I would actually, instead of leaving that alone, I'm going to distribute that because it'll make it so much easier, less chain rules to do. So here, not so much. This is much easier to leave it this way. This one here would be much easier to have that. So we're going to have that to be 7,200. 7,200 T. And then on here, we're going to bring down the 2. And so we're going to leave the inside alone. And that's going to be a 1. So we took the derivative, we did the chain rule, we brought the 2, we leave the inside alone. And so we need to take the derivative of the inside and chain that on. So then I am going to chain on the derivative of the inside, which is just going to be negative 90. And so that is the chain rule. And so that is the derivative now. Okay, it doesn't look kind of nice there, but we're going to be able to rewrite it as this is in the numerator. And this one here is going to go down to the denominator. The 2 is already in the denominator. So we're going to have 2 square root. This one here is positive now because we brought it down. 3,600 t squared plus the 30 minus 90 t quantity squared. And this is just going to stay on the top. So we're going to distribute combined like terms. And it turns out to be 23,400 t minus 5,400. So that's what the equation is there. And so we want to actually find the minimum distance. So we're going to take that and set that equal to 0. The denominator, I'm going to multiply this denominator to both sides. So that's going to cancel on this side, and that's already 0. So we're going to get this to be 23,400 t minus 5,400. And then when you solve for it, we're going to get that the time is going to be approximately 23 parts of an hour. And so that's what we get for the time, but that still didn't answer the question. So being able to answer the question here is, hold on. Okay, so being able to answer the question is that we know at time equals to 0, y is equal to 0, x is equal to 0, and z is equal to not 0, but 30. Because if we go back on here, here when we have this value here, if x is 0 and y is 0, then we're going to get 30 left over. So that's what we know that z is going to be. 0, 0, 30 is left over. Okay, so we get z is equal to 30. And then we know that the maximum, this is when t is 0. When t is approximately 0.23, that's going to be the shortest distance between them at this time. And so we know that when we put that back into my equation, so when we go back over here and we put that into this equation right here where y is equal, that's the time, times 60, and then the time times 60, we end up getting y is going to be 13.85 miles. X is going to be and this is all approximately 20.77. And then when z is equal to 30, we're going to get that z is approximately 24.96. So when I go back and put those values in, I am going to get that to be there. So this is the time there, 24.6 miles is what we have. So to go and answer the question, if T is approximately, and you should write that as a sentence, the minimum distance between the two cars is 24.96 miles. And it is at, we really don't need that. The minimum distance between the two cars, and it is happening at T equals to 0.23 hours, which if we actually look at it, it is 13.8 minutes. And that the minutes make more sense than the hours on there. You just convert the hours into minutes, and that's how you do that problem on there. Okay, very good.